Hi, my name is PJ Renda, and this is the SnowMaker control system. So some background real quick. So SnowMaker produces artificial snow by combining compressed air and water under specific atmospheric conditions, typically measured with a wet bulb temperature below freezing, or typically a wet bulb temperature below freezing is what causes snow to get made. The actuators used for these SnowMakers are valves to control water flow rates and airflow rates. And the sensors used are temperature sensors, ambient and wet bulb, humidity sensors, flow meters, and pressure sensors for the compressed air. So some more background. Wet bulb temperature is the absolute lowest temperature that water can acquire before freezing. And it's calculated using the ambient temperature, which is just the air temperature, and relative humidity. The lower the wet bulb temperature, the better snowmaking is. And for the most part, a wet bulb temperature below 28 degrees Fahrenheit will produce snow. So software/hardware integration. Good performance is defined as producing snow that is not too wet and not too dry. I'll quantify that later. If the snow is too wet, it will not freeze and it will just be water on the ground. And if it's too dry, it actually will evaporate, and because of it, atomization is way too high. PID controllers will be used to adjust water flow and air pressure based on temperature and humidity inputs. The inputs to the system are sensor data, and obviously the sensor data is also the temperature and humidity inputs. The outputs are valve positions and snow quality. So system model. So deriving the system. The system uses physical properties for both air and water. Bernoulli's equation and the continuity equation will be used for the air and water flow rates. And wet bulb temperature equation is used to convert the humidity and ambient temperature into a wet bulb temperature. Experimental data, so system response to step changes in air pressure or water flow should be measured. And time constants and delays of the valves should also be measured to accurately model the system. This system can be simplified into a first order system with the delay to approximate the the continuous/discrete math, controller tuning, a PID controller with gain tuning based on the system model, which is the relationship between the snow quality and the wet bulb temperature. The Ziegler-Nichols method will be used to tune the PID. And as for nonlinear concerns, there are actually a lot of those with this model because there is no linear relationship between snow quality and wet bulb temperature due to the variable air pressure and water flow rates. Because of that, a simplified version of the SnowMaker will be used where a linear relationship for that can be found. And another nonlinear concern is that water lines in the actual SnowMaker can freeze while in use. Okay, so the wet bulb temperature equation is right there. It's a lot, and it's actually something that's argued over. No one really knows the exact equation because it's all found experimentally. And there's a chart of the ideal wet bulb temperatures. Anything below 27 will produce snow. Even 27 will, 27 degrees Fahrenheit, I should say. And then ideal snow quality is S equals 0.5. That's just quantifying it. So the range of snow quality here is 0 to 1, with 0.5 being the best right in the middle. Like I said before, 0 is very dry snow and 1 is extremely wet. Okay, so this is the simplified Simulink model. Basically what's going on here is you have three different inputs into the system, one being the wet bulb temperature, which has that equation included inside of it to use the ambient temperature and the humidity. Then you have the water flow and the air compressor flow. Both the water flow and the air compressor flow have their own separate PIDs because they have to be tuned separately due to that non-linear relationship, this is the best way I could make it. Then all three of those signals go into a block that, or go into a function that then adds all of them together and weights them separately, so that outputs snow quality, and that's where I linearize this. And then that's all fed back into the system again, and yeah, back into the feedback loop. Okay, so tuning the model. Unfortunately, the Ziegler-Nichols method could not be used to tune the model. This is likely due to a poor model design, or just having two PIDs made it so tuning it was not very simple. So I then went to heuristics, and I employed those to tune the model as best as possible. And as you can see, I get the quality of snow right around that 0.5 range that we were looking for. It's not perfect, but it's at about 0.6, which still produces good quality snow. All right, system development. So some concerns are the nonlinearity in the system. Again, makes using PIDs difficult. There are minimum air pressure requirements that were not really considered in the system. Like if you have too low air pressure, the water's not going to atomize and the snow's not going to form. And it doesn't optimize snowmaking. This just optimizes the quality of the snow being produced by the SnowMaker. And some troubleshooting. Honestly, I would scrap this design and move to a PLC, programmable logic controller, just because there's a lot going on in this system, and PLCs can process more information faster and they aren't as simple as PIDs. You can tune them a lot easier. And some consequences for automation. Over-reliance on automation could lead to failures in unexpected scenarios, requiring robust fail-safes and operator training, which gets to the next point of most modern-day snowmakers are automated, but they're heavily monitored to avoid problems, because if anything goes wrong, that can be expensive. Something freezes in the pipes and it's just broken. All right, why this should be included in the class. So SnowMaker control system uses multiple engineering disciplines, including heat transfer and thermodynamics, which is not something that we cover too much in class. It also uses fluid dynamics as well with the flow rates. It's challenging system to model, so that's another thing. And if modeled correctly, it could be good practice for tuning PIDs. And yeah, that concludes the presentation.